We're back to astrophysics, and I'm going to do a problem. And this is kind of a connection to a previous problem. We looked at the gravitational field using Gauss's law for gravity for a solid uniform density Earth. Now I want to do it for a non-uniform density Earth. So suppose I have a planet, and it's not real, right? Because no planet would have this. But the planet has a mass r, m, and a radius r, but it has a density ar. So the density of the stuff, it's higher closer to the surface, right? Because as you get r increases, and you have a zero density in the middle. So number one, what is the value of a to make this work? So that has a mass m. Number two, what would the gravitational field be like inside and outside of the thing? Now I'm going to do the first part. I'm going to find a, and then I'm going to use Python in my numerical model to model 1,000 points, 5,000 points, whatever I want for a non-uniform density. And so it's kind of tricky, and we can talk about that in a second, but let's find the value for a, get to it. Okay. So I want to find the value of a in this density function such that the total mass is m. Well, there's a trick I can use here, and the trick is that I can create, since the density only depends on r, I can integrate by breaking this into tiny little shells. And if this shell has a radius r and a thickness dr, then the volume of that shell would be the surface area of the sphere multiplied by dr. So that's a little trick. It doesn't really seem like it'd make it work, but it does work, right? Because if dr is super, super tiny, I don't have to worry about the shell, the volume of a shell. I can just take the area multiplied by dr. So with that, I can calculate the volume of that shell. dv, I'm going to call it dv. It's going to be the area of the sphere, 4 pi r squared times dr. So that's my volume element. Now, I know that density is mass over volume, so mass is going to be density times volume. That means the mass of that element, dm, is going to be rho times dv. So that's going to be a r 4 pi r squared dr. Now I can just integrate both sides, and if I integrate this side, I get the total mass. And I integrate the other side, I'm going to say it's the integral from r equals 0 to capital R, a 4 pi r cubed dr. So that's not too difficult to integrate, right? So that's going to, I can bring the 4 pi a, and then I get r to the fourth over 4 from 0 to r. So m is going to be equal to, the 4's cancel, a pi r to the fourth. So a is going to be equal to m over pi r to the fourth. Let's put that over here. A is m over pi r to the fourth. Okay, so now we want to model this numerically by making some random points. And we have a problem. And the first problem is I need to actually measure the density. Suppose I make my points, I want to know if I'm right. So I want to kind of calculate the density of my creation. Okay, so let's start with the sphere that we have. So in the previous code, which I will link the video down below, I took a sphere, and it's made up of, let's say, 5,000 points. Like that. And I did that by creating a random number between negative r and r in the x, y, and z direction. And then I just cut off the ones that weren't inside the sphere. Okay, so not a big deal. Well, I need to make a function that goes through and counts, essentially counts or adds up the mass of each of the piece. So here is a section. I need to pick a section. And let's just say this is r temp to dr. And what I'm going to do is just go through and say, if there's, for each of those masses, if its radius is greater than r but less than r plus dr, then I'm going to add its mass to the total. And then I have the total mass inside of that little shell. And then I divide by the volume. So the volume of the shell, I'm going to use the volume is 4/3 pi r plus dr cubed minus r cubed. So because if I have a super, super thin shell, I might not get any masses in there. So I don't want to have it super thin. If it's not super thin, then I want to use the real volume for the shell. Okay, so I have my program. I'm going to jump to the program. We're going to change it, and I'll give you a link, of course. And we're going to build a density function for my uniform density planet. So here's my uniform density planet. I think this is 5,000 points. You can rotate it around if you want. And then I plotted right here the gravitational field as a function of r, and we showed that it was linear in the inside and 1 over r outside. That doesn't even look right. Let's run it again. It looks kind of not as good as I would expect. It's random, so every time it's a little bit different. Okay, we're just getting this spike there. So you could eliminate these spikes, because what happens is you go through and add up the gravitational field due to each point. If you're super, super, super close to one, you get a super, super, super high gravitational field. So you could just like cut those out. It'd work a lot better, but we're not worried about that. Okay, let's modify the code. Let's call this just gravity. I want a title that's reflective of reality. And I'm going to plot rho versus r. That's what I want, rho. But other than that, I'm going to leave it the same. That's 5,000 masses right there. G, I don't need. RS is my list of points in the sphere. Right, that's my 5,000 points. So right here, that's what this does. This goes through, it calculates a random vector between negative r and r, and then it says if that vector is, the magnitude of that vector is less than r, then add it and count up everything like that. So, and then this stuff right down here just plots the gravitational field, which I don't want to do, so let's just comment that out. Comment, you got to end it with a comment too. Okay. Now what I want to do is define rho. And I want to give it a value of r and a value of dr. So let's call that rr and drr. And I don't like to reuse words, symbols, that's why I did that. Now I'm going to use, I don't want to pass to it my list of values. I'm going to use my global list of values, which maybe it's a bad idea, but life is full of bad decisions. So let's just use that bad decision. So I have that rs. So let's go through all the values in rs. Each mass has a mass of m over n, right? So I'm going to say for r temp in rs. So it's going to go through the list and call it r temp. And now all I want to do is to see is the value in my shell. So if mag r temp is greater than rr and mag r temp is less than rr plus dr, then it counts. So up here, actually, I need something else. Let's put this m shell equals 0. So if it's in there, I want to say m shell is equal to m shell plus the mass of that, which is just dm. They all have the same mass in this case. We're going to have to change that later. But other than that, that's it. Now all I want to do is to calculate the volume of the shell. So v shell, I'll call it vs. It's 4/3 times pi times rr plus drr. Aha, I just caught myself. You guys are supposed to catch that. Plus drr cubed minus rr cubed. Now I can return the density, return m shell divided by vs. Let's try it out, right? Let's just test. So I'm going to print rho at 0.5 times r, and let's say r over 50. I'm just picking a value. Okay. And let's see what we get. Because it might not work. Okay. 5, 3, 5, 1. And this is for the Earth. So let's just print out the density of the whole Earth just to be clear. I can put that up here because you do have to have this function. If I'm using that rs list, I have to have the function after I make the list. Otherwise, it's like, I don't see a list. I don't know what you're talking about. But I can calculate the volume, the density of the Earth. Let's do volume of Earth. V Earth is going to be 4/3 times pi times r cubed. And then rho Earth is m divided by v Earth. And let's print that. And I'm going to leave off the units just because I want to get all this stuff done. Okay. So that should be around the same thing. Okay, now let's just move our value of r and calculate the density and then make a graph of r as a function of rho as a function of r. So I already have a graph listed up there. I already have my function. I don't need this anymore. So now let's say RT, I use that up there. Let's say RTT is 0. And then DRT, temporary RT, is going to be how far do I want to move in each step? Let's say that's R over, what did I use before? R over 20. So I'll have 20 data points from the middle of the planet to the edge. While RTT is less than R, then what I want to do is just to plot the density. So let's plot the density. F1.plot, the density is going to be rho of RTT DRT. That's it. Oh, I need RTT. Right, I need to plot the R value and the density. And now I need to increase my value of RTT. RTT equals RTT plus DRT. Let's see what we get here. There we go. So down at the bottom, you're always going to get this weird stuff, right? Because there's not that many points because my volume is super small. I don't have a constant volume integral. The very, very first part, it's super tiny, so it could be 0, right? I start R with 0, so that's just a 1/120th, so it may not get anything. But other than that, you see here that this is a constant density, and it's 5,570 or something like that. So pretty legitimate along with the other version. But now we want to make a non-uniform density. So the first idea I had was to try to distribute these point masses so that they're favoring the outside rather than the inside. And there are ways to do that. You can have non-uniform distributions of masses, but it's tricky. So instead what I'm going to do is to keep a uniform distribution of masses, but I am going to have each of the points have a different mass. So dm is not constant. Instead, dm is going to be the density, which I can calculate as a function of rho, which I'm going to have a different one, but that's fine, times the volume. And so they'll have a constant volume now. Each mass has a constant volume, and we'll calculate the mass. Okay. So let's do that up here. So the first thing I'm going to add is this A thing, right? Because I calculated A. What was it? It was m divided by pi times r to the 4th. So that's my A. Now I want to also I have V Earth. I need to calculate dV. So dV is going to be the volume of each element, and it's just going to be the total volume of the Earth divided by the number of pieces. So this will be V Earth divided by n. So instead of my dm, which I'm going to get rid of up there, I can leave it, but I don't. Yeah, let's just leave it. I don't think I need it. Now what I want to do is associate a mass with each point. So one way to do that is instead of adding vectors to my list, I'm going to add the sphere to the list. And then I can associate the property of mass with the sphere. So here I make the RT, and then I make the sphere, but what I want to do is just to put this in the list. So RS is going to be a list of spheres. So it's going to be sphere position equals RT, radius equals, let's make it a little bit smaller, R divided by 150. And then I'm going to give it the property mass. So the mass of that's going to be the volume times the density. So the density is A times mag RT, right? That's AR. That is my density. And now I just need to multiply that by a dV. So then that gives me the mass of that piece. Now I can refer to the things as this is the position of my sphere and this is the mass of the sphere. So they don't all have the same mass. And I'm not going to do that right there. Okay, so now I made that. I do need to change this function though, because this function assumes R temp is a vector. So what I want to do instead of say R temp is now a sphere, so I need to say the position of that and the position. And then down here, this is fine, except I'm going to add to it R temp dot m, which is the mass of that piece. They're not all going to have the same piece added to them. This is fine, except that's fine and that's fine. Okay, I think it should work. I think it'll work. Maybe I should save it. Okay, so now let's go to play. There we go. It worked. So I do have a linear density, right? You could find the slope of that, but we don't really need to. It should be, the linear density should be A, and everything is good. But it looks the same. It looks the same because I still have the masses distributed in the same way. Okay, great. Now we need to find the gravitational field inside and outside of the sphere. So let's jump back to the board and do that. Okay, so let's just erase this. So let's start with the gravitational field outside the planet. So remember, oh, that's a bad circle. That's not that much better. So remember that we have the following. Gauss's law for gravity says that the integral of g dot n hat dA is equal to negative 4 pi g mn. I had to remember that for a second. So this says that the flux of the gravitational field over the surface is equal to 4 pi g times the total mass inside of that closed surface that we have right there. And we only want to do Gauss's law for situations where we know something about the symmetry of the field. In this case, we know it's spherically symmetric. So outside of this, if I pick another sphere of radius r, then the gravitational field should have a constant magnitude over that surface, and it should be perpendicular to n hat along that surface. So n hat's actually pointing out. So if I integrate g dot n hat, or g dot n hat over this whole thing is going to be negative, just negative g. So I get negative g, the magnitude of that, times the integral over dA. And that cancels. Now the integral of g, the g times the integral of dA is just the surface area of that sphere, which we know. So it's going to be g times 4 pi r squared, 4 pi g. Now what's the mass inside of my sphere? Well, it's just the total mass of the whole thing, which is just going to be m. So now I solve for g. I get g, that cancels, that cancels, that cancels. I get g is g m over r squared. And that's the gravitational field due to a point mass. The magnitude, we already assumed the direction, right? So we don't need to reassume the direction. We've already picked that when we did our integral. So that's pretty easy. So let's write that over here. G out is going to be equal to g m over r squared. So anytime you have a spherically distributed mass, it's as same as, once you're outside the mass, it's the same as though all that mass was at the origin of point mass. Okay, now what if I want to go inside the sphere? Now we have a different problem here. So suppose I go here, and this is r now. So I still have assumed spherical symmetry. I still assume g is constant. I still assume g is perpendicular in the same direction as n hat. So this integral is still going to be g times 4 pi r squared, right? That's still the flux. The only difference is now this is my mass n, so I'm going to have to find that. So let's say that's 4 pi g mn. So I can find the mass in mn just like we did before. It's going to be the integral of rho dv. But we did that. In this case, it's going to be from 0 to r. And I probably shouldn't do that, but I'm going to do it. So it's going to be rho is a times r. This is going to be the integral of a r, and then dv. What did I say dv was? It was 4 pi r cubed dr. All right, we did that. That's what we did, right? See, the shell is 4 pi r squared times r, and then times ar. No, it is r squared dr. That r came in there. Okay. From 0 to r. So I can find the total mass as a function of r. So mn is going to be equal to 4 pi r to the 4th over 4. That's it. Times a. Now, let's go ahead and put in our value for A. Right, that cancels. Yeah. So this is going to be m, it's pi r to the fourth, m over pi r to the fourth. So mn is just going to be equal to m r to the fourth over r to the fourth. OK, now I can put that in up here in Gauss's law. These cancel, and I get g out. No, this is n. Gn is going to be equal to g times the mass n, which is m r to the fourth over r to the fourth, divided by r squared. So I get g m r squared over r to the fourth. Now, a couple things to check. What does this say the gravitational field at the center of the object should be? Well, it should be 0, right? Because the density is 0 there. There's no mass, and so you're inside of a sphere, and there's no mass inside of it, so it should go to 0. This also goes to 0, so that's pretty good. Next, what about at the surface? At the surface, the two functions should agree. So if I put in r equals capital R, I get gm over r squared, so that's good. So it should work out fine. Let's go ahead and make our plot of the gravitational field as a function of distance using the numerical calculation and see if we get something that looks like this too. Okay, so let's switch back over here to Python. Now I'm going to make a modification. I'm going to change this to g. And I'm not going to plot right here this. Oops, let's put it right here. I can leave that one there and just delete this one down here. And let's go back to the function that plots. Now we're going to have to make some modifications. Because we've already have our masses and everything like that, right? They all have their own mass. So this is going to say Rm and Rs, but Rm is now a sphere. It's not a vector. So this is going to be Rm.pos. dg is going to be, dm is going to be actually Rm.m. And then that's fine, that's fine. I think it should be fine after that. Yeah. Let's see what happens. Could be a disaster, you never know. Okay, I think it looks fine, right? R squared, 1 over r squared. That's a win. Okay, that's the end. So if you want homework for this, you could look at, and I'll put a link to this video down below, you could look at the object orbiting our masses and one tunneling through and see if they arrive at the other end at the same time. Spoiler alert, I said that if the mass doesn't have a uniform density, then they wouldn't get there at the same time. Think about which one would get there first and then model it and see which one would happen. It's not too hard. You can really just modify the code from the previous video. I'm not going to do that right now. Maybe I'll get bored and do it, but that's that for now. Link to this code down below, link to the other videos down below, and I will talk to you later at the end.